bit of background about myself. My degree is in mechanical engineering, and during my engineering career, I've used a lot of 3D CAD applications, from SolidWorks to Inventor to Rhino, which we're going to talk about today. So I have a pretty good amount of experience going back and forth and kind of seeing how each one of them operates. All right, so like Sophia mentioned, this is what we're going to cover today. This is a lot of stuff to go over. I'm just going to say that right off the gate. I'm definitely going to glaze over some things. Not going to go into that much detail on some topics that you might want. Of course, that's what the courses are for, and you can always ask questions on anything that you would like further clarification on. So, where does Rhino fit into my workflow? A lot of times I get questions of what should I use, Rhino or Revit, or Rhino or AutoCAD. The truth is that there's a right tool for the right job. So where Rhino is strong is in several areas that Revit and AutoCAD are not necessarily as well versed in. One is that it's very flexible. So you can use it to explore different forms, fabricate unique organic shapes. Really, the sky is the limit for Rhino. One comparison that I like to use is, I like to think of Revit as a toolbox, essentially, with a bunch of different tools and a bunch of different parts that you can take out and put together in different ways. And there's a lot of different parts and there's a lot of different ways you can put them together, but ultimately you're limited to those parts. Whereas Rhino is kind of like sketching something on a pen and paper. You are only limited to what you can imagine and what you can, draw to the extent of your abilities. So that's where practice makes perfect in that sense. But Rhino is also very adaptable, so it can read and write in just about every 2D and 3D file formats, except for some proprietary ones, but it even does some proprietary ones. For example, FBX, which is a Revit / 3ds Max file format. So we're going to touch on that later. It's also really expandable. Rhino is very powerful right out of the box, but with the amount of plugins you can get, its capabilities are nearly endless. So some that we're going to go over are V-Ray, which is one of, if not the most powerful rendering engine available for utilizing ray tracing and other cutting edge rendering techniques. It also has some BIM plugins like Visual Arc and Rhino BIM, which allows for even greater integration with Revit. For example, you can set different categories and families, and you can have them directly importing and exporting back and forth. And most of all, Rhino's fast. So Rhino lets you iterate really quickly to arrive at your final design. It's not limited by constraints like Revit might be. It's a very, very flexible and quick program. So first we're going to touch on Grasshopper, which is one of the new features integrated into Rhino version 6. No, it's not this Grasshopper. I had to do it. So Grasshopper is a visually scripting tool. It's essentially a form of visual programming, and it's a way to automate all of the 3D modeling and organization processes within Rhino. So instead of clicking buttons and menus to run operations on a 3D model in Rhino, you can use Grasshopper to link these commands together. So you can see this little slider, let's say, is connected to this radius input, which then creates a circle on this plane, and then that outputs to here, and you can have a whole string of essentially functions that will work together. So imagine the process of modeling a fence, for example. First, you might start with the path that it is going to take, and then you might make some of the posts, and then you might want to make some of the, forget exactly what they're called, but the other little posts that go perpendicular to the posts going vertical. So with Grasshopper, you can kind of describe this process algorithmically and link parts of it together. So we're going to actually show you an example of that here on this slide. And let me just, there we go. Okay. So on the right, you'll see my my Grasshopper program, function, algorithm, whatever you want to call it. And on the left, I'm drawing a curve in Rhino. Nothing fancy, just a nice interpolated curve. Back in Grasshopper, I'm going to right click, and I'm basically going to tell that function what to look for. And there, automatically you can see it already generated the geometry that I defined based on that curve. Right, so this is the fence that I was talking about. Now you can see I'm changing the height, and you can see the representation update in real time. Bear with it, it's a little slow. I have to render all of that. Changing the rail separation. You can also change how granular you can get. You can see the rail separation over here is units of 0.4, whereas distance among posts, you can go down to 3 decimal places away. So you can see that kind of updating in real time. And now I'm going to change it so that it is fully shaded. So there is our post. And kind of going over here, I'm going to show you some of the different functionalities and parameters that you can set. Now it's starting to get a little silly, a little big, but I think you get the idea of what is capable, what Grasshopper is capable of letting you do in Rhino. So instead of having to model this fence every time you wanted to make a fence, you can just have this Grasshopper algorithm and generate whatever geometry you want for a particular project. And here I'm going to show you another little example of some maybe a more organic type shape, something that like you might see at a architecture art installation or something, for example. So let's go ahead and take a look. So lofting that curve and creating this curved structure from it. So that's just a few of the examples of the capabilities of a Grasshopper within Rhino. Really, the possibilities are endless, and you can kind of use it to automate and automate any process or kind of general 3D geometry that you might use frequently, doors, windows, etc. So importing, exporting, and make 2D functionality. So interoperability, getting Rhino and Revit to play nice. Sometimes when you're trying to go back and forth between the 2 programs, feels like you're trying to jam a square peg into a round hole. Doesn't really work sometimes, or at least it doesn't work the way that you might want it to, or that you might expect it to. For example, going from Revit to Rhino, you'll notice the things that look great in Revit are kind of messy in Rhino. You'll have things that are dangling. You'll have walls not connected, things like that. And then even going from Rhino to Revit, the geometry might come in perfectly fine, but if you want to change it, if you want to dimension it, doesn't always work. So we're going to go over some of the tips and tricks that we've come up with to kind of make that process a little bit easier. So first, I should state that the methods used by Rhino and Revit to represent geometry are fundamentally different. That's why you get so many cross-compatibility issues. So Rhino is NURBS-based, which is mathematical representation of the 3D geometry. NURBS stands for non-uniform rational B-splines, which, like I said, are mathematical representations. They can accurately describe any shape from a simple 2D line, circle, arc, curve, whatever, to the most complex 3D organic free-form surfaces or solids. One of the most important features or qualities that NURBS has that makes it ideal for CAD is that it's very precise. Like I said, it's all mathematically based, and it's also an industry standard. So its cross-compatibility is pretty broad as far as that's concerned. Now, Revit, like I said, uses predefined families of objects that contain the 3D parametric data, and it cannot directly manipulate an object's individual polygons. So that's what I was referring to when I said that Revit is kind of like a toolbox, or even like a Lego set, for example. It's got a bunch of different shapes, but it can only do those shapes, and you cannot, break a piece off, or you cannot necessarily, modify them as easily as you could in Rhino, or at least not with the flexibility that you could. On the left, you'll see basically the difference in how Rhino and Revit interpret different splines, right? So you'll see these points over here are the points that define these curves. The Rhino curve being the black one, the Revit curve being the purple curve. And you can see that it's fundamentally different based on these same points, the way that it creates slightly different spline. And you can imagine expand that out over, hundreds, thousands of different splines. Well, things are going to get a little bit off. So on the left, again, you'll see some, basically from the slide previous, the natural extension of that, which is to show the difference in how it interprets the different surfaces, right? So you'll see a Rhino NURB surface up here, and then right below it is the Revit loft form. And then kind of comparing the two together on the bottom, you'll see that where the color is the strongest has the highest surface deviation, and where the color is softest, it is the lowest surface deviation. So you can see that, like in this curve, which might be more easily defined, not that much difference. But then as you start to get to the extremes, the deviation starts to increase dramatically. And then you can see over here, similar thing. It just is a representation of the way that they interpret these different geometries. Some important file formats to be aware of. As you're going from back and forth, you're going to run into several of these. ACIS or .sat, which can be exported by Rhino and imported into Revit. 3DM, which is the Rhino native file format. So that's just the format that's read and written by Rhino. As of version 2017, Rhino can actually open and read 3DM files. Of course, there are some limitations there. IFC, which if you use Revit, you might be more familiar with. Rhino does not natively work in IFC, but there are some third-party plugins that are available that will let you define layers and materials and objects, basically, and export them using IFC. And then Revit can read that IFC file and kind of know where to put everything. And STL, which is one that you all might be familiar with, which is stereolithography. It uses triangles to describe the surfaces of an object. And it's the most common file format for 3D printing, though it does have its limitations. It is a very old file format, but the extension of that is it's a very well-known file format. So there are pros and cons to each one of those. So the truth is, there's no best way to work between the programs. I'm sure it would be nice if I could come up here and say, this is the way to do it. Don't do it any other way. It'll work every time. That's not the case. What we found is that really the best way to do it is to kind of work backwards. Know where you want to end up before you start. So, to that extent, like going back to using the right tool for the right job, certain things Revit is very great for. Certain things it's not. Same with Rhinoceros. So knowing when to use which tool and how they're all going to work together is something that you should think about based on your project from the start. So here's an example. Only exporting the necessary parts of the model using the right tools, right? So you can model floors, walls, windows pretty easily within Revit, right? So you can kind of just make all of your simple geometry. But if you want a really complex curving roof, or if you want some sort of organic form that, let's say, you make in Rhino, don't make the whole thing in Rhino. Just make that roof and export that individually that you can bring into your Revit, instead of making the whole thing in Rhino and then saying, how do I get all of this to play nice within Revit? So you can see me go through that those steps here. You can create the site plan, walls, etc. in Revit. If you want to use that as reference, you can export it as an FBX or even DWG, DXF, which Rhino can also read. load that into Rhino, and then you can design the geometry based on those dimensions. Define or design your roof, your walls, your curved surface, whatever you want to do in Rhino. Export just that geometry as a SAT ACIS file into Revit, and then you can place it or manipulate it within Revit the way that you might want to. All right, moving on. You've got your model, you're all done. Now you want to 3D print it for the site plan, right? So there are several ways that you can go about it. Option one is to drastically increase the thickness of all the geometry in Revit before exporting. Why would you do that? Well, let's say you have a wall that's maybe 8 inches thick in real geometry. Scaled down to the size of 3D printer, that 8-inch wall becomes paper thin and not going to hold up for 3D printing. Additionally, you're going to want the model to be watertight, this is the biggest problem that I've run into trying to 3D print and process models that come out of Revit, is that any sort of modeling or design anomaly or imperfection is going to be exacerbated 10 times when you start to try to 3D print. So if walls aren't joined properly, if geometry isn't placed flush with certain surfaces, you're going to see it. Things are going to fall apart. I've had situations where a wall will not be connected to the roof geometrically, and you try to print it and you remove it from the printer, and all of a sudden the roof just separates completely from the whole model. All because a little tiny gap appeared in the 3D representation, which is not something that necessarily you would see when you're working, in Revit, but when you try to print it at that scale, will definitely become an issue. So that's why you would want to go back. Basically, you want to make a totally separate model just for the purpose of 3D printing, right? Because you don't want to blow up the actual walls. You're not going to make, two foot thick walls on any structure, save for a bomb shelter or, something like that. So you're essentially making an independent, totally separate model that is solely for 3D printing. Another option would be to add in place mass geometries that are offset in the building, and then you would essentially Boolean them together and export as STL. I should mention that Revit has a free plugin for version 2019 and definitely some previous versions as well. That is called the STL exporter, which essentially just takes the geometry of whatever is in the 3D view that you're currently in, and you can export it as an STL. That's all it does. It doesn't clean anything up. It doesn't connect anything, but it at least lets you export that and then natively work on that within Rhino, or in this case, or whatever other program you might want to use. You can kind of see a representation of that on the right-hand side. Over here, you see this is the original Revit model with all of the rendered and modeled windows and chimneys, etc. Over here, you have the in-place mass representation of that model. And here, you have that kind of being combined together. All right. Now, some important things to consider when you're working for or designing for 3D printing. One of the most important is units. Most 3D print programs work in millimeters. Keep this in mind. You can always convert or scale, but it can be a bit awkward. You can change the units, and Rhino will provide a conversion. But again, you are best working natively within the units that you're going to end up printing in. Right. So tolerances as well. You can see tolerances available over here too. Good rule of thumb is that your absolute tolerance should be the printer tolerance times 10. So if your printer can only print to a resolution of 0.1 millimeter, then your absolute tolerance is going to be 1 millimeter. A lot of printers can print more precisely than that, so you'll be looking at like 0.1, 0.01, but this is a good rule of thumb to keep in mind when you are designing and setting your units and tolerances. Most important is your model should be watertight, and within Rhino, that means it is a closed solid poly surface. What does watertight mean? It means if you filled it with water, it wouldn't leak. So as you're modeling, keep that in mind. Check for the closure after every surface command that you make. This is the number one reason that most 3D prints fail. It's the number one reason that it takes us sometimes several hours to prepare a model for 3D printing, which is connecting all the surfaces, checking, for interferences, etc. So like I said, check the model. These are two important functions to keep in mind when you are evaluating a model for 3D printing. Cell bad will identify bad surfaces or objects, and then you can extract them, just like extract bad surface. Extract bad surface will identify and remove the bad surface from the poly surface for rebuilding. So once you've done all of that, you can rejoin the surfaces together, verify that it is valid a closed poly surface, and then you would look for the best orientation for export. Obviously, this is going to be different depending on the printer, depending on what you're printing. For example, this roof, let's say, you might think that it would be best to print it just totally flat on the printer. And you wouldn't necessarily be wrong, but what is going to happen is if you're using a traditional FDM or MakerBot style 3D printer, you're going to get a lot of support on the bottom, supporting these different curves and ridges. And that surface is not going to be very smooth. It's going to be, you're going to have like a lot of overhangs. It's not going to be a good surface for printing. So probably the best way to orient this for printing is to print it on one of its sides like this and add a raft or brim in the beginning to support that. So, but again, this all comes down to what the model is, what it's going to be used for. Maybe you're going to put this on top of a building, so you don't care about one side of the surface. So that changes that parameter. So it's really more about knowing, like I said, where you want to end up before you start, so that you can prepare and design accordingly. So before you export for 3D print, you're going to create a mesh of the object for the STL file, which is essentially triangulating the surfaces and exporting a file that has a representation of all of those triangles as points. So here's some things to keep in mind when you're going through this process. These are some pretty good starter settings just to start off right off the bat with. Anything that's set at 0 is turned off. So you see we have density, aspect ratio, minimum edge length, and maximum edge length all off. It's best to try one at a time before deciding how you want to proceed. This way you'll know exactly what effect or impact each setting has on the resulting polygon. So the most important parameter of this menu is the maximum distance edge to surface. And what this does is it forces Rhino to create a mesh that is no further away from the surface than the specified value in current file units. So if you're working in millimeters, this is going to be in millimeters. Keep this in mind if you're working with a structure from Revit, for example. If the imported geometry is in feet or inches, and you set your max edge length to 1, that's going to be 1 foot or inch, not necessarily 1 millimeter. So this is just something to keep in mind. What this does is it lets Rhino use fewer polygons in the lower detail areas and more polygons in higher detail areas, which makes the resulting mesh more efficient. Like I said, this is the most important setting. So if you would change anything or it should be that one. That is the maximum distance edge to surface. That's over here. A few other of the parameters. The maximum angle parameter forces more triangles in sharply curved areas, similar to max distance edge to surface, but a little bit more specific. Using this, small features that fall below that max distance will be subdivided into smaller chunks, essentially. You might be able to get away with a little bit bigger of a max distance by letting the angle setting take over in some cases. So, but this is something that is more for tweaking than for overall generally creating the mesh. And additionally, the minimum initial grid quad setting, that makes sure that flatter areas have enough polygons to look smooth. Sometimes the way, if surfaces are a little bit off, the triangles might create some weird looking facets, and minimum initial grid quads just makes sure that if it's relatively planar, it keeps it looking smooth. Okay, so now we're going to do a quick, hopefully quick, V-Ray rendering demo. So let me switch over to my Rhino, bring that over to the screen. You might remember this shape as the Mobius type shape that we generated with our Grasshopper algorithm previously in the presentation. You can see it kind of represented here. You can see my little studio light box background all set up from here. And actually, let me bring over my my V-Ray window so that you all can see that too. Pull that over here. Okay. Great. Get rid of some of that. So here's my V-Ray window. So first thing that we want to do is we want to set the material for this object. So let's go into V-Ray, and we're just going to use the some of the preset or pre-made materials that are baked into V-Ray. I think it'd be cool if we do something metallic, so that way we can see the reflection. We can see how light, changing the light impacts the way it renders. Let's see what would look cool. I did gold before, so let's go with gold again. Let's go with shiny one though. Let's go with 24 karat gold, right? Why not? Now let's go ahead and hit that render button over here. Let's see what we come out with. Okay, cool. So it's going to render basically the view that you see in your viewport. What is pretty cool is that if you go over here, you can change your to V-Ray Interactive, which will let you see in real time how your different changes end up affecting. So like, for example, let's say we want to change the way the lighting is set up. So we can change the intensity, maybe not as intense, more intense. So one neat thing to do is you can change the color of the lighting to a more, maybe a softer color, blue, or even a yellowish color. You can also go in the render settings and you can say, okay, what would it look like if we change the exposure? Oh, that's a little overexposed. That's why I usually don't mess with that. But essentially, this is a good way to see how the different options will affect your render before you dedicate the resources and time to setting up a full render. Again, not going to hit everything that we might want to hit or that we would hit in a more extensive class or something of that nature. But I think you can kind of see what capabilities the V-Ray has, how powerful it is, and really, all of the different options you have available.